Enthalpy. All right, in the study of chemical thermodynamics, enthalpy is one type of energy. There are plenty of others that we'll be talking about, and most of those will come up in a later chapter. But thermodynamics, I mean thermo meaning heat, which we more broadly think of as energy. Dynamics, so the change of it, it's in motion, it's not static, it's changing, it's flowing from one thing to another. Right? Thermodynamics, and specifically chemical, involving chemical reactions. Okay. The book defines chemical thermodynamics as the relationship between heat, work, energy, and chemical reactions. So I think that makes sense. Now, there's many different types of energy in thermodynamics. The basic one that we should start talking about is internal energy, symbolized by a capital U. Some books will symbolize this by a capital E as well. I think maybe U is more common. All right, internal energy is just the total or the sum of all the energies that that substance has. It might have potential, it might have thermal, maybe it's got electrical, I don't know, but if you add them all up, that's the internal energy of that. For us, there's going to be two basic ways that chemical reaction can have energy, and that's the heat. Should they say that they could have it? Two different ways that we'll see it change, okay? And that is the heat and the work done by that reaction. So notice I don't have just U, I have delta U here, the change in internal energy. So if I add up all the different types of energy a substance can have, before and after, so initial and final, right? Where did that type of energy go? Well, it had to flow in or out of the substance, just like we had the heat flowing in and out before. And so what they're saying is, hey, whatever that change is, it's going to come out as heat, and another way it could come out as work. You see, I could push against something, I could cause something to move. That's what happens in gasoline burning in the car. It's pushing against the pistons of the engine and it causes the car to move. That's doing work. The car is not necessarily getting hotter, but it is being put into motion. And so work is another way that we can absorb or release energy. So the change in internal energy, where does it go? It flows out as heat and or perhaps work. That is described as the first law of thermodynamics. Another way of saying the first law of thermodynamics is that you're not creating energy, you're not destroying it, it's just flowing somewhere. You're just putting it into a different form. Right? And in this case, again, it's flowing in or out as work or heat. The book has this picture just to summarize this idea. You've got your system, this green circle, and you've got this surroundings that the system is living in, if you will. And if the change in internal energy is negative, that means it lost energy. That energy went somewhere. Or if it's positive, that means it's gained energy. Okay? And if the system is losing energy as heat, then Q is going to be negative. If it's gaining it as heat, then the Q is going to be positive for that system. Now, what about work? Same idea. If I'm expanding, if I'm pushing against a piston in the engine, because I'm the system, I'm the gas, I'm the reaction that's burning the gasoline, producing gas, pushing against the piston. All right. If I am the system, then I'm pushing against that piston, then I'm doing work on my surroundings. I'm doing work. I'm losing that energy. Work, W, would be negative for me. Conversely, if I'm the piston, and the gas is pushing against me, causing me to move, then I am gaining that energy. It's going to show up as kinetic energy because now I'm in motion, right? So I'm gaining that energy. They say work is positive for me because I'm absorbing it, I'm getting it. Right? So again, the same idea, plus or negative for both Q and W for work, whether I'm gaining it or losing it. Now, what is enthalpy? Enthalpy is another type of energy we can talk about that a system might have. Enthalpy is defined as U plus PV. That is the internal energy plus the pressure times the volume. Now, we haven't talked about gases yet, right? But PV, we'll see in upcoming chapters, is the pressure and the volume of a gas. And if it changes, so change in U plus the change in PV, then that means either the pressure or the volume of that gas is changing. Maybe it's getting bigger, maybe it's getting smaller. And as I put a certain amount of pressure, or I should say if a gas exerts an amount of pressure over a change in volume, That's like pushing against a piston, and we're going to see later that pressure times volume is actually equal to work. Or more specifically, the change in pressure times the change in volume is equal to work. Alright, so delta U over here we already defined as Q plus PV. And so I'm just expanding out what this equals, U plus PV. Now delta U is delta PV, Q plus W plus the change in pressure volume. If I'm at constant pressure, then this is a constant, it's not changing, and so I don't have to have it on the inside of my delta sign, I can move it to the outside, and that's what happens here. Sorry, I jumped ahead here. I took my pressure and I moved it outside here. Over here I've still got QP and WP. I put those little P tags. In thermodynamics, if you put a little subscript, that just means that that thing is being held constant. So here I've got heat at constant pressure, work at constant pressure. Work is defined as the negative pressure times the delta V. You don't need to know that now. Again, this is the idea that an expanding gas does work on its surroundings, and that work actually equals the pressure of that gas times the change in volume. All right, you don't need to know that now, but we're going to go ahead and use it just to show you. I'd have a negative P delta V, a positive P delta V, and that cancels out, adds up to be 0, which means I'm left with just Q, heat. All right, so this thing called enthalpy, which we define, or we symbolize, as H, or the change in enthalpy would be delta H. We defined it as the internal energy plus pressure times volume. That works out to be nothing more than heat itself, as long as the pressure is being held constant. And if I'm a chemist and I'm working in the lab, I'm essentially under 1 atmosphere of pressure, and over the course of that experiment, a couple minutes, that atmospheric pressure is not going to change much, so it is constant. So here I have this type of energy called enthalpy, which is nothing more than heat. The heat of whatever is happening, the heat flowing in or out of that chemical reaction, as long as I'm at constant pressure, which I am. All right. So that's the big thing. We always are going to talk about enthalpy. We define it as U plus PV. It's symbolized by H. For a chemist, we can almost always take that to simply mean heat. Okay. All right. Again, this is what I've got here in my notes in this red. Perfect for chemist. Here's a reaction. Hydrogen gas plus oxygen gas. That's a combustion reaction. Produces water when you combust that. I've balanced it here. Got a 1/2. Why did I balance it as a 1/2? Because I'm looking at what is the heat or the enthalpy change when I do just 1 mole of hydrogen. So I wanted a 1 in my balanced reaction here. Therefore, this had to be a 1/2 in order to get that to balance correctly. And you're going to see this very often. If we have a reaction and we're interested in one thing combusting or one thing reacting, we'll balance it so that there's a 1 in front of that. It makes it a little easier. We'll get more about that later here. But okay, so here's my balanced reaction. The heat, that is to say the change in enthalpy for that reaction, turns out to be a negative 286 kilojoules. So in other words, when I take 1 mole of hydrogen and I combust it, maybe I did it inside of a calorimeter, someone did it inside of a calorimeter, they measured that heat, right? 286 kilojoules was given off by that. Now yeah, when I burn things like hydrogen, I do release a lot of energy, a lot of heat, so it's not surprising. This is an exothermic reaction. The heat, that is to say the change in enthalpy, is negative 286 kilojoules for that. Well, what if I had twice the amount of hydrogen? Well, I'd get twice the amount of heat. And this is what I did down here. Let's multiply through by 2. So 2 here, 1/2 times 2 is a 1. This is a 2, so I've got twice as much. It's still a balanced reaction, but now I don't have that fraction anymore. I've got whole numbers, right? Here it is, but look at my delta H would be, well, twice what I had before, so negative 572. So if someone tells you what the change in enthalpy is for a reaction, they have to tell you specifically what that reaction is and how they wrote it. Did they write it like this top one here, in which case it's only 286? Did they write it like the second one here, case 572? Makes a big difference. So they've got to tell you what that actual reaction is. Also, the states are very important. You see, if I take this reaction and I use liquid hydrogen, that's pretty hard to come by. But instead of gas hydrogen, well, guess what? Liquid versus gas, they have different intermolecular interactions, different rotations, vibrations, and such. The amount of heat is going to be different when I burn that. Or in this case, in my green down here, I've got that same reaction, but here I'm having it come out as steam, as gas. Okay. Well, that's a different product. Again, a different ability to absorb or release that heat. The heat of that reaction is going to be different. Up here, when I did it, it was 286. If I keep it as a gas, actually it's 242, a different number. So you got to be very, very careful with your reactions, how they write them, and make sure it corresponds correctly to the delta H that you're going to use. All right. Example 5.9. Let's go to the textbook and find that one and see if we can't put this in motion. We can apply this. Scrolling. 5.8. Here we go. 5.9. A gummy bear, yay, which is essentially all sugar, sucrose, table sugar, sucrose. 2.67 grams of this sugar. All right, so that's how much this gummy bear weighs. That's how much sugar, and sugar C12H22O11. It reacts with potassium chlorate. That's actually an oxidizing agent. It's going to oxidize that sugar and metabolize it, essentially. That is to say, it's going to combust it. All right, 7.19 grams of this potassium chlorate. I wouldn't expect you could predict that reaction, but here it is. Sugar, sucrose, right, plus the potassium chlorate gives you carbon dioxide, water, and potassium chloride salt. This is obviously done in water because it's aqueous and aqueous, and so the salt's still aqueous. The water, liquid, just adds to the water that's already there, and the CO2 comes bubbling out as a gas. So I can kind of picture what's happening in this reaction. It says 43.7 kilojoules of heat are produced. So if I did this reaction inside of a calorimeter, I can measure the change of temperature of the water. It would have gone up, it would have increased, and I could figure out exactly how much heat that water absorbed, Cm delta T, right? And in this case, it turned out to be 43.7 kilojoules. Okay. It says, determine the enthalpy change for this reaction. The heat for this reaction. All right. Now keep in mind, I don't have exactly 1 mole of sugar. I've got 2.67 grams of sugar. Right? And again, I don't have 8 moles of potassium chloride. I had 7.19 grams of potassium chloride. All right, so they wanted to take this data with that amount and figure out, well, how much heat would have been if I had exactly 1 mole and 1 there. All right, let's go back to my calculations. I've rewritten the equation. I'm telling you, we're getting heat. In this case, we're getting 43.7 grams of heat, 7.19 grams of potassium chloride, and 2.67 grams of sucrose. Got 2 things reacting. I've got 2 different amounts where the perfect amounts match perfectly, or is one in excess. One of them is a limiting reactant. Well, probably the case. We better figure that out. So that's the first thing I did. What is my limiting reactant? And as you know, you can always define or figure out limiting reactant by converting to moles first and dividing by the coefficient in the balanced reaction. So I did that for sucrose, 0.0078. I did that for potassium chloride. See, I'm dividing by 8 because that's my balanced reaction, 0.00734. Hey, just a little bit less. So actually the potassium chlorate is what I'm going to run out of first. That's my limiting reactant. I'm going to have a little sugar left over at the end, still in that beaker. Okay, now that I figure out my limiting reactant, I can go through and do this calculation. Right? The amount of heat, delta H, right, per the moles of potassium chloride I have here, which in this case 8 moles. Here I'm talking about the balanced reaction. See, this is what they want me to solve for. What would it be for that? But it's not for just any old amount. It's for, in this case, 8 moles of potassium chloride. Right? That would equal, well, let's see, on the top I need heat, 43.7. Look, I made it negative because I know it was exothermic. Divided by, on the bottom, I've got the amount of potassium chlorate. Well, over here was 8 moles, so I got to get moles over here. I had 7.19 grams, and I converted it to moles here. 122.5 is the molar mass of potassium chloride. Right. If I solve that for delta H, which means I'm going to divide this and then multiply my 8 over, I get negative 5,960 kilojoules. Let me go back and review that because that could be a little confusing. Right. This is, first of all, the delta H for the reaction as it's written in the normal way 1 mole of sucrose, 8 moles of potassium chloride to give you those products and some heat. Okay. How much heat? 5,960. So I could call that 5,960 kilojoules per, go back up here again, per 1 mole of sucrose. 5,960 per 8 moles of potassium chlorate. I could do per 12 moles of carbon dioxide produced, or you're always saying for this reaction. So negative 5,960 kilojoules per reaction. Reaction as it's written here. Right? But I don't usually look at the whole reaction. I look at something specific in that reaction. In this case, we were looking at the potassium chlorate. So per 8 moles of potassium chlorate. That's why when I was comparing the numbers, I had delta H per divided by 8 moles of potassium chlorate, because that's how it is in my balanced reaction up there. I've got an 8. Okay. That equal then, here's the actual data from the lab. I want, again, heat, kilojoules, per how many moles of potassium chlorate. Now over here it was just 8, because that's how it was in the balanced reaction. Here's my actual data. The actual amount of heat I measured, 43.7 kilojoules. And what was the actual amount of potassium chlorate I had? Well, I converted that over to moles down here, 7.19, and then divided by 122.5. So here is the reaction side, the balanced reaction side, if you will. On here, here's the actual data that was collected. Well, nevertheless, the heat per mole of potassium chloride doesn't matter if it's from the reaction or from the actual lab data. They have to equal each other, and so I could put them equal to each other and solve it finally for delta H of that reaction. All right. Standard state. The standard state of something is simply a set of commonly accepted conditions. Those conditions being as simple as possible, essentially. Standard state, pressure-wise, is 1 bar. 1 bar. Now, it used to be 1 atmosphere. I think about 20 or 30 years ago they changed it. And some textbooks still say 1 atmosphere, so watch out for that. This textbook correctly says 1 bar. Standard state is 1 bar. If you ever have to convert, by the way, 1 atmosphere is 1.01325 bars. So the unit of an atmosphere, that's a unit of pressure, and bar, those are almost the same. Look at 1 is 1.01, almost the same. All right. And again, we'll get to more of that in the gas chapter when we talk about it. But okay, 1 bar of pressure. Solutions are exactly 1 molar concentration. That's just what we call the standard state, a standard solution. Most solutions are not going to be sitting there at 1 mole, and so when we do calculations, we always have to keep that in mind. We're probably not at the standard state. However, you see, when we list values, thermodynamic values, what is the delta H of this reaction or of that process, we will often list them in the standard state just so that they're comparable. And you can always take those values and do little tweaks, little calculations to go away from the standard state to whatever concentration you have, perhaps. So we're going to see how that works. But anyway, 1 molar is the standard solution concentration. Temperature, room temperature, 25 degrees Celsius. Now, interestingly enough, the temperature is actually not part of the standard state. Not officially, but very often you'll see tables listed and they'll say at the top of the table, hey, at 25 degrees Celsius, because that's room temperature. And some of these values could change if you're not at standard state, or I'm sorry, if you're not at 25 degrees Celsius. So again, we could do tweaks on the calculations of whatever we're trying to figure out. All right, but standard state, 1 bar, 1 molar, unofficially 25 degrees room temperature. Okay. If we're listing these thermodynamic values at their standard state conditions, we put a little naught sign as a superscript. So delta H naught. That little naught, I can interpret that immediately as meaning, oh, I'm at 1 pressure and my concentrations are 1 molar. All right. Very often, if they include that temperature, they'll put it down here, 25 degrees Celsius, which, by the way, if you convert to Kelvin, is 298. So delta H naught 298, that simply means what is the heat released or absorbed for that chemical reaction when you're at the standard state, when you're at 1 bar, 1 molar, and when you're at room temperature. All right. If they don't put that stuff on, so delta H, well, that's just the change in heat when you're at any old condition. whatever the temperature is, or whatever the pressure, or different concentrations, that's the delta H under those conditions. Right? So we'll very typically see these things listed under standard state, and then we have to make the slight correction. All right. So first of all, a couple examples for you here. The standard enthalpy, so delta H with a little naught sign, right? The standard enthalpy of combustion. They put a little C down there, meaning, okay, we're going to combust things, reacting with oxygen, burn them up. Often you'll see this as the heat of combustion, because remember, enthalpy, as long as you're under constant pressure, is heat. Here's a table of standard molar enthalpies of combustion. Alright, so hey, look at all my reactions. Yep, they're combustion reactions. Taking something, combining it with oxygen to get a product. Often, almost always, I don't know if there's any exception to it, a combustion reaction will be exothermic, so it's going to release heat. And if you look at my delta H's, they're all negative because they are losing that heat. They are producing it, and that energy is flowing out of them. Okay. The units here, kilojoules per mole. All right, so that's heat per mole. So these are not per gram; these are per mole. And it says right there, hey, it's at 25 degrees Celsius. It's also got that little naught sign, which means I also know that they're listed at 1 bar and 1 molar concentrations if these things were aqueous. Now, it looks like to me they're not. There are some liquids, but they're not aqueous, so it doesn't actually apply in these particular reactions. I can use those then to calculate the amount of heat or the amount of substance if I know the amount of heat, that kind of a thing. So example 10. Scroll ahead here. It says use figure 21, or as figure 21 suggests. Alright, here we have a big burn going on the road. Gasoline must have been spilled and it's combusting. The combustion of gasoline, highly exothermic. Yeah, we knew that. Okay. Let us determine the approximate amount of heat that's produced when you burn 1 liter of gasoline. That looks like a lot more than 1 liter, but okay. 1 liter of gasoline, assuming the enthalpy of combustion of gasoline is the same as isooctane. So octanes and isooctanes, that's what gasoline mostly is. It says the density of isooctane is 0.692. Well, I bet I'm going to need the delta H for that. So if I look at my table up here, I look down here, here's isooctane, so basically gasoline. Here's the chemical reaction. For 1 mole of gasoline or isooctane, which is C8H18, combining it with oxygen, I get the products of CO2 and water. As it's written there, negative 5461 kilojoules per mole. Per mole of what? Again, well, it's per 1 mole of isooctane, or it's per 25 half moles of oxygen, or it's for producing per 8 moles of CO2, etc., etc. Okay, so how am I going to do that? They want me to calculate the approximate, well, let's determine, the approximate amount of heat. All right, let's go back to my notes. Here I've rewritten that. 1 liter of gasoline, C8H18. Density is 0.692. They gave me that. What is the heat? All right, 1 liter, convert that to milliliters. That's 1,000 milliliters. All right. Why am I doing this? Because I'm going to try to figure out how many moles we're talking about. So I can use the density to get to grams, and then use the molar mass of C8H18 to get to moles. So at this point, I've got moles of isooctane. And then they said it was negative 5461, and that's per 1 mole of isooctane, because again, remember, that's the reaction as they wrote it. So for every 1 mole, that's down here, right? They wrote that as a 1. If I wanted to go, if this was moles of oxygen, I would have to have a 25 halves down here, but they've got a 1 here, so that's why I put a 1 down here. For every 1 mole of isooctane, I'm getting 5461 kilojoules of heat. So just like the stoichiometry problems or all these other problems that we do, we're just lining them up, canceling the units, putting them in where they need to be. That all equals negative 33,100 kilojoules. A lot of heat given off. That many kilojoules for every 1 liter of gasoline that burns.